In what universe is simple regression simple? It's true. All right. What goes into building a linear model of the world? I'm not going to read through all of the objectives for today, but I am going to talk about this one that is in bold. So your primary job is this one. Conceptually interpret all output, including relationship between values. So as I mentioned, we start in this class just with interpretation, and then we get into like the decision making and model building. So at some point today, we're going to look at a model fit table, and it's going to have a bunch of numbers in it. And we're going to look at a coefficient table, and it's going to have a bunch of numbers in it. Your litmus test of like, do I understand the lecture today, is can you look at every number in both of those tables and conceptually understand what they are and explain it to somebody else. I highly suggest you just derive or generate some simple regression tables after class, whether it be in office hours or with other people, and practice doing that. If you can't do it with simple regression, you're going to be lost when we get to multiple regression, because it changes a little bit when you get to multiple regression. So square up today's stuff before you get to the next stuff next week. The other thing that is important today is the concept of centering. So I would say those two things are probably the most important things coming out of today. All right, so we're going to talk about moving from correlation to simple regression. We'll revisit the GLM, which you already know. We'll dig into all of the pieces of simple regression, and then we'll do a quick demo. And as part of these two sections, we will talk a little bit more in depth about how to write up an APA results section, with a reminder, which I will remind you again, that APA doesn't govern narrative. So I'm going to show you one example of how I might write up a result section, but it is not the way to write up a result section, because the only thing APA governs are the stats. You can play with how you present this story. Now, in a simple regression, you can only get so creative. There's one predictor, but as you get into model comparison, you're going to get a little bit more creative about how you want to write up your results section. So correlation, we've got Pearson R, coefficient of determination, little r, or as we're going to much more commonly see, big R squared. I'll show you why it's big R squared and not little r squared as we get through to models today. So from correlation to regression. Correlation, I think I said at the very beginning of lecture on Tuesday that there are kind of three purposes of regression overall: describing, explaining, and predicting. Describing really belongs kind of square in the land of correlation. So describing is literally a descriptive stat. It's not predicting anything in the population. It's not explaining a phenomenon. It's describing how strong and in what direction two variables are related. When we move into prediction or explanation land, then we're in regression. So we're modeling, in that case, we're modeling the real world. We're saying, using theory, this thing leads to this thing. We're not proving that statistically, but we're using theory to model causality in that way. And we're doing it using the general linear model, which we did in regression, but we're going to be actually using the general linear model equation a lot in regression in a way that we didn't in ANOVA. So a reminder that the GLM is a framework that models an outcome variable as a linear combination, an additive linear combination. So predictor plus predictor plus predictor of predictor variables. So outcome equals predictors plus error. So if I'm measuring exam score from time of day plus hours studying, if the model predicts your exam score should be 6 and your exam score is 7, then your actual exam score of 7 is a function of time of day, hours studying, and then that error term. Who remembers this? That was a good face. Nobody? 2 of you? I don't believe that. I really want to know who remembers this. It's important, because otherwise, thank you. So mx plus b, m is a rule. It's the rule for the relationship between x and y. It's the slope It's also known as a coefficient. Most algebra teachers don't teach it as a coefficient, but that's what it is. It's rise over run. So as x goes up, what happens to y? It represents a change in y for a 1 unit change in x. And most importantly, it's the rule for everyone. There's one n that applies to everybody. B is the y-intercept. It's the value of y when x equals 0. mx plus b is a linear model. Y is a linear in x. So all we're going to do is rename this. We're going to rename it like this. B sub 0 plus b1 x1. Now, we're swapping. Notice we swapped the order so that the intercept comes first and then the slope. Does that matter?
No.
No. Is 2 plus 3 the same as 3 plus 2? Yeah. We just always write regression equations with the intercept first. And for some reason in algebra, they like to write mx first and then b. Who knows why they do that? Maybe to screw with you when you get to grad school. I don't know. But notice nothing's different here. B1 is the rule for x and y. It's the slope. It's the coefficient. These are what we refer to as coefficients. They represent the change in y for a 1 unit change in x. When I say unit, what unit? Say that again.
Whatever the unit of x is.
Good. It's an unstandardized, this is important, it's an unstandardized raw unit of x. So if we're measuring weight in pounds, it's as x goes up by 1 pound, how much will y change in whatever y is measured in? B1 is the rule for everyone because we created one line that fits best for all the data points. Oops. And B sub 0 is the y-intercept. So it's the value of y when x equals 0. Now that's kind of, I'm glad I sort of picked weight because it's going to foreshadow where we're going to get to in a minute. So it would be the value of y when somebody weighs 0 pounds. That's kind of weird. Nobody ever weighs 0 pounds. Hold that in the back of your brain. We're going to solve that problem. B sub 0 plus b1 x1 is a linear model. It's the simplest regression model we have. This is a simple regression model. Why is it simple? Because it has one predictor. So here it is. Here's a simple linear regression model. B sub 0 plus b1 x1. X and y are variables, meaning they can vary. They can take on different values. Are b sub 0 and b1 variables? Victor, why not?
This year, they're calculated based on.
But more importantly, why are they not, why can't they be different? Why don't they change? They're what? They're the rule for everyone. In stats terms, we call those fixed parameter estimates. Remember what we're doing in stats. We are estimating relationships out there in the population. So what we're doing when we look at this B1 is we're saying that's our best guess. That's our estimate of the relationship between X and Y out there in the population. That's our parameter estimate. And it's fixed because we're determining one parameter estimate for everybody. Now, when you get more advanced in stats, you can run models where instead of having fixed parameter estimates, you can have random parameter estimates. Now, random parameter estimates don't actually mean random. They mean different people can have different values. So you can run a model where you have what's called fixed slope, random intercept. And that would look like you let everybody start at a different place, but they all have the same rule in terms of the relationship between X and Y. You can also have random slope, random intercept models. Those look like this, where each person has its own starting place and their own trajectory. We're not going to run those. We're doing fixed intercept, fixed slope models in here for regression. That comes way later. But I want you to understand that because I want you to understand the terms fixed and random. Because sometimes when you read in the literature, those are the terms that they'll use. I ran a fixed model, or I ran a random intercept or fixed random, fixed intercept, fixed slope model. Good so far? So this is the overall simple regression model. But remember that line, this equation, so oops, this line, this equation is the prediction line. It's the line that works best for everybody. It's the rule we figured out that works the best for everyone. But not everybody's score is gonna fall on that line. It's gonna be a great line for some people, and some people are gonna be off from that line. So the model's gonna over predict for some people, and it's gonna under predict for other people. This is what it looks like when we plot the line with people's actual scores. What is this? Doing what I want you to do. What's this? Error, exactly. That's error or residual. So if I'm asking about someone's individual score on Y, it's the intercept. Everybody has the same intercept, it's fixed. It's that person's Y or X score times the slope coefficient, fixed for everybody, plus their individual deviation from that line, their error. Error is also a variable. It's unobserved. It can vary. Some people are going to have a lot of error. Some people are going to have a little bit of error. Some models are going to have a lot of error. Some models are going to have a little bit of error. The less error you have in your model, the better your model. That's the goal. The goal is that we have a model that has the least amount of error variance that we can. Why? Because on the positive side, the goal of stats is to explain as much variance in our outcome as we can. Variance that we cannot explain is the stuff we don't want. We want to be able to shrink that as much as we can. So here is what a full, simple regression model looks like. Y equals B sub naught or B sub 0, you can call it either one, intercept, plus B sub 1, X1. So coefficient times variable X plus error. Now, you won't always see it written with the error term, but you'll always know that that error term is there. If there were actually no error term, that would mean every single person's score lies directly on that line, which never happens. Huh? Cool. Any questions so far? Questions online? We can also have multiple regression equations. Only difference in a multiple regression equation is that we've added in a second variable. Here I called it Z. Sometimes we just call it X2. It doesn't matter. Variables can vary. We could call it, I don't know, we could draw a happy face. It's just a symbol. And we have two rules. We have what happens in the relationship between X and Y, controlling for Z, and what happens to the relationship between Z and Y, controlling for X. And if we want to plot that, which I'm not going to make you do multi-dimensional plots because they're very hard to visualize, it would look like this. In this case, Y and X and Z and error are variables, and our intercept and our two coefficients, or two slopes, I should say, are fixed. All three of these are called coefficients in a regression equation. This one's an intercept, and these two are slopes, but they're all coefficients. Cool? Coefficients just means constant in math terms, as in they're fixed. Emily.
And X and Z are the predictors.
Correct. Yep, X and Z are our predictors. I, for simplicity's sake, will just call them X1. So B1, X1, B2, X2, B3, X3, just to keep it simple until we get to moderation, and then I'll mess with you. Cool. Questions so far? We're not going to do this until next week. Good. So really, we're going to dive straight into an example. This is data light, so we're not going to like look at all the data. We're not going to do demo style, but really, like I said, the purpose is vocabulary, the regression tables, and anatomy of a regression line. Like, how do we make it, and what do all the pieces of the regression table mean? So we're still going to go through a model building process, like always. Start from the beginning. For folks who are new, everything in here we do through model building. There's a model building guide online. It's called Building Golem. If you want to know the story of why it's called Building Golem, I'm happy to tell you, or they're happy to tell you. Did I tell you what I got for Christmas? One of my former students gave me a golem. It's in my office. I'll bring it on Tuesday. It's very cute. I mean, it's ugly, but that's kind of thus making it cute. So model building process, I'm gonna give you backdrop on the research study and then we'll dive into the data. It starts with observing real world phenomenon. So I'm just gonna read this to you because it's pretty small. So we've got a developmental psychologist and it's working on an adolescent therapy program. And they notice that self-esteem of clients seems to impact their recovery process. She knows self-esteem is complicated and she's curious about factors that predict or enhance it, specifically ones that are within her control. And it seems that clients that participate in her group sessions are more self-assured and experience more success. So she wonders if social support of peers has an impact. Don't laugh. Social support. Yes, it's coming back. So she generates the following research question. How does social support impact self-esteem of adolescents? After a thorough literature review, she theorizes that the social support individuals receive from peers help reaffirm their sense of self-worth. She also theorizes that it helps individuals reframe setbacks as less pervasive, personal, and permanent. That's Sugman's. Thus minimizing the negative impact on self-esteem. So her ultimate hypothesis, i.e. her model in hypothesis form, is social support positively relates to self-esteem. Notice her hypothesis is not causal. She's not running a causal study. She can't say anything like social support causes increases in self-esteem. Really, your two best options when you're doing a correlational design are positively relates to or is positively associated with. The reason I like positively relates to better is because I have a pet peeve around passive voice. And is associated with is passive voice. If you're taking directed research with me, you'll figure that out quick. Is associated is passive voice. Relates to the subject, social support, should be actively doing something, which is positively relating. But you could use is associated, that's totally kosher. It's fine, really. In hypothesis, it's fine. So she designs a cross-sectional, that means at one time, correlational design, meaning she's just gonna collect data via survey, using survey methodology to measure the perceived level of social support and self-esteem of 15 patients. PSA, she should have used a power analysis to determine the sample size, because 15 is not enough. The reason I did 15 was so we could look at all the data on a slide. Got it? That's it. All right, data collection and preparation. So to get to know her data, she's gonna look at her raw data. She's gonna look at her descriptive stats, her scatter plot, her residual plots, and correlations, which is another form of descriptive stats. She's gonna clean her data. So she's gonna handle any variables that are named something funky or far too long. She's gonna look at any weird values, any duplicate entries, so same like participant ID, data classification, so changing anything from character to factor that needs to be changed, taking out outliers, dealing with missing data. She's gonna check assumptions. So she's gonna investigate whether her data meet the assumptions of simple regression. So normality, histogram, skew and kurtosis, linearity, looking at scatter plots, and then homoscedasticity, she's gonna look at her residual plots. So plots of her error, and then she's gonna run a Bruch-Pagan test, which is actually testing whether that error is constant across all levels of her predictor. And we'll look at that in a second. She's also probably gonna do this. It's not totally linear. So generally what it looks like is I'm gonna look at my data. I'm gonna clean it to some degree, like probably any variable issues or duplicates. Then I'm gonna check my assumptions first, at which point I might then like take out outliers or clean it a little more. And then I'm gonna check assumptions again. One mistake that people often do is they check assumptions and then they mess with their data a little more and they don't check it again. You have to check assumptions on the final model you'll be running an analysis on, even if you check it initially. That makes sense? So we're done with that part. All right, so here we have some descriptives. So we've got a mean social support of 4.87 with a pretty decent standard deviation. Self-esteem is 4.07, and we can see that they're correlated at 0.54. Do you have a marker? Oh, there, if you're online, I want you to write 0.54 down. We're just gonna remember that. So that's the what? Yes, it's the correlation, but what's the actual terminology? The Pearson R. So that's the R. I just need one. I just need that to remember this. Thank you. So that's the Pearson R. R equals 0.54. That's the correlation between social support and self-esteem. It's gonna come back in a second. All right. Specify. Remember that we can specify models in lots of different ways. We can specify it as a hypothesis. Social support positively relates to self-esteem. We can specify it as a diagram. Social support relates to leads to self-esteem with our error term pointing at self-esteem. So the idea is we've got 100% of the variance in self-esteem to work with. That's explained by one of two things: social support or error. We can write it as an equation, a regression equation. Social support equals B0 plus B1 support plus error. We can even simplify this down and write it as like Y equals B sub 0 plus B1. You just want to do an S or SUP plus error, or you could just call it X if you really wanted to. Or we could specify it in R. Self-esteem regressed onto social support. These are all what? All four of these are models. Good. They're just models in different languages. Right. Good. So they're all visuals of our model. All right. Now we're going to get into the new stuff. We're going to specify, we've specified the model. Now we're going to estimate and interpret it. This is the piece that's probably the most important from today. How do you actually estimate and interpret simple regression models? So when we estimate parameters, remember we're estimating parameters in the population. The first thing we need to do, and this is good vocab, like filing, like file the vocab here, because that will be helpful for your APA write-ups. So the first thing that we do is we fit our model to the data, okay? We sometimes say that we condition our model to the data. Either of those are fine. So we say, here are our data, here's our model. We fit our model to the data, and then we estimate parameters using some sort of estimation method. Okay? What does that really mean under the hood? We generate an equation with coefficients, those are the estimates, that best fit our data. That's in English. But the vocabulary is fitting our model to the data and then estimating population parameters or estimating parameters using some sort of estimation method. Cool so far? So how do we do it? Well, this is one of my favorite lines. It comes from Andy Fields' book. He says we do it using Nefwick, the line finder. And so there's our line. That line look good? What do you think? JJ, my favorite skeptic, is like, no. How about this one? Better? Well, what about if I drew one that was like, I don't know, like slightly to the bottom line is like, how do we figure out what the best line is? So the method that we're going to use, and the method that is always used in just regular straight up regression, the estimation method, is called ordinary least squares. Now, it's not the only estimation method out there. Once you get into advanced stats, like the structural equation modeling, you can use lots of different estimation methods. And when you can use lots of different estimation methods depending on what your data look like. So when your data are non-normal, you cannot use something like this. But for now, in regular regression, which assumes normality of some sort, normal regression uses ordinary least squares. What is ordinary least squares? It's going to select a line that gives you the lowest sum of squared deviations. So if you think about this data point, that's the deviation. Remember, some are going to be below, some are going to be above. If you square those and add them all together, that's the total amount of error that you have away from the line. OLS is going to give you the coefficients, the parameter estimates for the line that makes that sum of squares the lowest it possibly can. Got it? Yeah.
You mean like lowest, and I'm just like thinking about this visually, do you mean like absolute value from the line?
No, because you square it all, remember? So if this was like 3 below the line, and this was 1 above the line, well, it would be, this would be 1 below, and this would be positive 3, 1 and positive. This squared would be 1, and this squared would be 9. And so then you'd add 9 and 1, and whatever this one squared is, and whatever this one squared is, and you'd get some number, let's say 42.
Oh, I read.
But if I drew a line like this,
Yeah.
then the deviations would be like this, 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 this. That number would be way bigger.
And then in like in the different ways to think about it, there's like 1,000, right?
1,000 data points.
1,000 data points, it would take the one with the lowest, so the deviation squares.
Yeah, no matter how many data points it is, it's gonna put the line where the sum of all the squared deviations is as low as it can get it. It's gonna generate like parameters until it gets that line to be the lowest sum of squares possible. Yeah,
Oh,
yeah, no. FYI, for when you read articles and when you get into other stats classes, or if you're taking factor analysis and SEM now, which a couple of you are, when data are normally distributed, OLS, ordinary least squares, produces the same parameter estimates as maximum likelihood. So maximum likelihood is another estimation method. It's essentially equivalent to OLS when our data are normal. You don't need to know that now, but you need to know that so when you read an article that says we estimated parameters using maximum likelihood, you're like, oh, that's like the basic way. And then that way, when you get, like, for example, when you get up into higher stats and you have non-normal data, you can use things like robust maximum likelihood, or generalized least squares, or weighted least squares. There's all sorts of other estimation methods out there. But regular regression, which is what we're doing all through C, assumes normality and requires, therefore, only uses OLS unless you mess with it. Cool, questions so far? So the only estimation method that you're responsible for being able to explain is OLS. Yeah, who was that? Is there a question? Oh. Is it possible to find ordinary least squares? I feel like I need to nominate, it's gonna be AJ if I do it. I feel like I need to nominate somebody from online to be the question reader from chat, because I can't get to chat because it's on the other side of the screen. AJ, can you read that for me?
Sure. Is it possible to find ordinary least squares without the modeling of a computer? Probably suck.
Well,
Can you
we
find,
calc-
can you get,
we
I don't
calculated sum
know.
of square, we calculated sum of squares. It's just the sum of squares, isn't it?
no, because that wouldn't give you the coefficient. No, that doesn't give you the coefficients. I don't think so.
It's like, how could you calculate ordinary least squares?
Can you calculate the coefficients by hand using OLS? I mean, there has to be a way because people did it before computers. I was gonna make a really bad joke, but I won't do it. Allison's like, don't do it. I don't know. Look that up, Peter. Is that right?
There's a method, but.
I'm sure there's a method, but it takes pages and pages of.
It says, why would you want?
ChatGPT says, why would you want to? No, but there has to be a way, but it's not as simple as calculating the sums of squares. Because it has to generate the coefficients as well. And you can calculate the sum of squares, but at this point, you're calculating the sum of squares once you already have the line. Does that make sense? Like the way I just did it was, here is the line. I know what the sum of squares is.
I'm trying to think, going back to what we learned last time, when you calculate the sum of squares, it's the smallest distance.
But that's from the mean.
From the mean. Okay.
That's for a single variable. Yeah, not for a relationship between two variables. But you will actually, I see what you're getting at, and yes, actually, just a second, you can. You can. He can. For simple regression only though. Hold on, hence what's on the board. Hold that thought. So we're gonna fit the line to the data by figuring out the coefficients or the parameter estimates of the line that minimize the sum of the squared residuals. Good so far with me? But we want to know how well does that line actually fit our data. So just because it's the best doesn't mean it's good. So here is the best line for this set of data. It's not very good. So the first question, so all of this previous stuff happens under the hood for us. And then we're gonna get two pieces of output. We're gonna get a model fit table and we're gonna get a model coefficient table. So essentially a model fit and a parameter estimate table. The fit table is gonna answer this question. So we got the best line, but how good is it? So here is a model fit table. And it's answering the question, how well does your specified model fit the data in your sample? And you're gonna see three pieces of information. We're gonna go through each of these pieces. So these two chunks, super important. The first is you're gonna see a null hypothesis significance test. How do you know? Because you see a test statistic, the F, you see degrees of freedom, and you see a p-value. They all go together. I put one box around all of them. They're all part of one thing. This is the model significance test. It follows an F distribution. It's asking whether your model fits significantly better than a model with no predictors. What is a model with no predictors? Say that loud. Say that louder because people can't hear you.
You just use the mean.
Good. If I had to predict someone's self-esteem and I had no information other than self-esteem scores, what would your best guess be? The mean. So what I'm asking is essentially, does it predict better than a model with nothing? Does it predict better than the mean? So it's testing self-esteem with nothing predicting it versus self-esteem with social support predicting it. The F statistic specifically is testing the variance of the model to the variance of the error, against the variance of the error. So how much variance is explained by the model relative to how much variance is explained by error. And the specific null hypothesis that we set for it is that all of the coefficients in the model are equal to 0. That would be no predictors. If we put 0, we've got an equation that looks like this. If we put a 0 here and a 0 here, then this entire part of the equation goes away. It's social support, or sorry, self-esteem with no predictors. Now, how often do you think we get non-significant models? Almost never, he says. Do you think anyone disagree? Why?
Really noisy data.
Wait.
Maybe it's really, really rare to get a non-significant model. Why? Emily?
You're nothing literature and theory.
No, it's not even that exciting. It's not because we have existing literature.
Because something is always better than nothing.
Exactly. Because knowing something, having some degree of information is often better than nothing. And how often, to pull in the theory part, how often are you building models where you're like, I don't actually think this predicts anything, but let's just throw it in. No, never. You're starting with models where you think they have some impact. And so the chances are they're going to predict better than a model with nothing. So even though we often put this in our model table, we don't give it a lot of attention. So to be quite frank, I will usually throw this in my model fit table and not even pay attention to it. Okay, sometimes, to be honest, I don't even throw it in my model fit table because nobody really cares. You put it in your model fit table, I just throw the R squared in. Yeah, so let's get to, yeah.
We have a question from the almighty chat.
Yeah,
So
thank you.
it's from Evan. He says, is B0 equal to 0 as well? Wouldn't B0 simply be a numerical value, seeing as the mean intercepts above 0? In this case, comma 4.
Read that one more time.
Is B0 equal to 0 as well? Wouldn't B0 simply be a numerical value, seeing as the mean intercepts above 0? In this case, 4. Evan, you can also probably.
If you centered it, it would be, yes. If you centered it, sorry, yeah, Evans, if you centered it, which we'll get to, it would be the average. Yes, you're Evan, yeah.
Next slide.
Next slide, next slide. End of this lecture. All right, let's get to the stuff that matters. This is the gold mine. This is where my eyes go first. Your R squared. Remember I told you you would, from now on, you would see it as a capital? This is the same thing. It means the same thing, but you will see it from now on as a capital. This is still the coefficient of determination. However, it is how much variance in our outcome can be explained by our model. Now, in the case of simple regression, how many things are in our model? How many predictors? One. So model and predictor are synonymous here. You see that? So saying how much variance in our outcome can be explained by our model is the same as saying how much variance in our outcome can be explained by our predictor. When we get to multiple regression and we have more than one thing in our model, then it's going to be how much variance in our outcome can be explained by our model, but we can't disaggregate which predictor it's coming from. It's always our whole model. So in the model fit table, this is referring to the whole model. In simple regression, those are interchangeable. Again, in a simple regression, it's the same as predictor because we only have one predictor. How do we calculate R squared? Regardless of whether we have one predictor or 8 predictors, it's a ratio of variance explained by our model to total variance in our outcome. So good variance to total variance. And how do we interpret that coefficient of determination? You know this already. It's here. How do we interpret that 0.29? Interpret it.
29% of the variance in self-esteem can be determined by social support.
Good. 29% of the variance in self-esteem can be explained by social support. Good. Now, when we get to multiple regression, it would be the more accurate would be 29% of the variance in self-esteem can be explained by our model. But in this case, our model is only social support, so that's perfectly accurate and actually more precise because we only have one thing in our model. Yeah.
So when we are talking about not just the regression and we do use model rather than predictor, when we're writing it up, do we list the predictors or just say model?
You'll get there. You'll just say model at the R squared level. At the R squared level, you'll say model, and then I'll show you in the coefficient table how to get it for a single predictor if you want. Yeah. What's left? R. What is little r is our correlation. Well, big R is just our multiple correlation coefficient. It's the relation, it's like a correlation between our outcome and all of the predictors. How many predictors are in this model? 1. So it's the correlation between our outcome and our predictor. What number did I have you write down before? Pearson R was what? 0.54. So the big R is also 0.54. It's just a correlation. It's just a correlation. It's not a commonly reported stat because once you get to more than one predictor, it's not super easily interpretable. If you have 4 predictors in your model and an outcome, and I tell you the multiple correlation coefficient is 0.26, what does that tell you? Not a lot. What does that tell you beyond what you get from R squared, which is how much variance you were able to explain by your model? That's like the whole point of stats, plus your individual coefficients, which we're going to get to next. The multiple correlation coefficient doesn't add a lot of value on its own. Some people will report it. The really, really, really important one here is the entire goal of stats is what? Explain variance in your outcome. What's the one stat that says how well your model does that? R squared. Here's a model. How much variance in your outcome were you able to explain? And when we start comparing models, that's going to be what we use to compare models. So in simple regression, big R equals little r because we only have one predictor. So what I did on these slides were we went one by one, but then I also created one slide that has all of it on one. You see that? So this is like your print it on poster size and put it above your bed to dream about it at night kind of slide. Okay. Yeah, I know you're going to do that. It's a great idea. All right, let's take a break And then the other most important slide, potentially more important than the last one, is interpreting the actual population parameter estimates. Let's do 10:05.
Yeah.
Jason, freaks up. When did she do the cross reg?
And also.
Yes.
There was what?
Some problem.
So it's like a single.
Yeah, so Natalie said we have not received the cross registration data file from Jason. We did receive a cross registration on 11/25, but it was for fall. That's a register for November. I wonder if Marisa accidentally wrote A and B on the cross reg file. No, the one she sent on November 25th. Because she sent one on November 25th. And that couldn't have been for A and B because you actually. Yeah,
There was an accident.
could you, how many people are like?
I sound like.
Worried about whether it's like fiber accommodation, like.
I think it's really.
Yeah, so now.
Yeah.
Yeah.
No, that's, it's, I do not. Right? I might ask, if they would refer to the ACB. Or, yeah. I would just say.
I think I say.
No, it would be, you would have to take it, and yeah,
Sometimes when I take notes, like, especially when I say,
Yeah.
yes, and look at
they already in here, I just didn't take this.
it. For now, I would say we just need to be like.
I think we've got time, because I don't think anything's going on.
Gia,
I'll just, we can get back to this week.
I get like that, like.
so we're having Zoom-ish with. Alrighty. So once we are done looking at model fit, specifically how much variance in our outcome can be explained by our model, then we want to investigate the individual model parameters. And here is what you get. So here's what an APA table looks like. This is a good model for your APA write-ups. You are always going to have two lines. You're going to have at minimum, you're going to have an intercept line, and then you're going to have a line for each predictor. So in a simple regression parameter table, you're going to have two lines. In a multiple regression table, you're going to have one line for each predictor plus the intercept. We're going to go through each of these. Our first value we're going to look at is the intercept. So this is these are both B's, this column here, but this specifically is B sub 0 or B sub naught. This is your predicted value of self-esteem when social support is 0. So when somebody ranks their social support as 0, we would predict their self-esteem to be 1.94. Questions? Why could that cause a problem? Well, how many scales go from 0 to something? Hopefully very few, because that causes problem. Nobody likes 0 inflated models. Usually scales go from 1 to something. Again, another issue like the nobody weighs 0 pounds. So again, foreshadowing, we're going to fix that coming up. All right. Next is our unstandardized regression coefficient. Unstandardized just means in the units, whatever you measured. So in the raw units you measured your variables in. So this says it's the slope of the regression line. So it's rise over run. It's the predicted change in Y for a 1 raw unit increase in X. So as social support goes up by 1 point on the social support scale, self-esteem is going to go up by 0.3 points on the self-esteem scale. Questions? I'm gonna pause after each one because this slide is like the slide. Ready for the next one? Yes, good. I knew if I waited long enough. Yep, yeah. So if you think about a graph, so this is positive 0.43. So let's say like it's like this. So what we're saying is this is social support here, and it's a scale. So it's 1, 2, 3, 4, 5. Let's say it goes to 7. As social support goes up by 1 unit on the scale, self-esteem is going to go up by 0.43 units on the self-esteem scale. Now, very important to understand that these are in raw units, which means if I give you this, you can't really draw it. Now, in this case, it's not super hard to draw because they're both on 1 to 7 scales. But let's say you are measuring like pounds and self-esteem on a scale. So pounds could go from like 0 to 100 and self-esteem goes from 1 to 7. You can't really draw an unstandardized slope because the scale is really hard to internalize in your head. We'll get to how do you draw it in a second.
I think Alan or somebody has a question.
Question, I can't see the chat.
Yeah, so the question is to clarify, would the 0.43 be the same thing as B1?
Yes. Yep, so we're gonna look at the whole equation in a second, but this whole equation would be Y equals 1.94 plus 0.43 X. Why is it 0.43?
It can be greater than.
Because it can be greater than 1. What happens if for every 1 unit increase in social support, self-esteem could go up by 3 points? That would be a crazy strong relationship, but it's possible. So unstandardized, B always has a leading 0 because B can be more than 1. All right, good. Any other questions? I always look at Victor. He has really good delayed questions. And he gives me the tell. He has like a thinking tell.
It takes longer for it to get through.
No, it's good. Let's go to the next one. Next one is standard error. We know what the concept of standard error is. It's essentially how off something is. Well, standard error belongs to B. So these two go together. Standard error is the variability of your coefficient. So remember when we started off with that MX plus B thing and we transitioned to, we just subbed them out for B1 and B0. We said those are fixed parameter estimates. Those are the rules for everybody. But that rule doesn't work for everyone. It works really well for this person, not as well for this person. Standard error is how much error you have overall. Whoa, well, that's not my kid's school. I'll call back if it is. Standard error is how much error you have overall in your coefficient. So essentially it's not really how well your coefficient fits, it's how poorly your coefficient fits. So the higher your standard error, the more the points vary away from it. So you're like this, so even if you had like a really positive relationship, if the points are like here, your standard error is going to be pretty big. Whereas you could have a low B, that's a very low slope, but maybe the points are like here, and then your standard error would be really small. Why do you think that matters? With my
In terms of predicting to the population parameters, you're going to be looking at your F, which is your variability that you can assign to your model versus the error.
good, so good, but I'm going to take it into this table, not the last table. So you want to look at what's the relationship. So this is what's the relationship. But then this is how well does that relationship work for everybody? And those two things together are gonna tell us, are gonna tell us whether that's a significant predictor or not. So even if you have a really strong slope, but it doesn't work for anybody, that's not a good predictor. And in fact, oh, why did I go there next? Should have gone to T next. I'll get there in a second. I saw a question. Yeah,
Can you say it again? So what's the relationship is the 0.43?
Yeah.
0.19 is how well does that work for everybody?
it's actually how poorly does it work for everybody. Think about that picture. That standard error is the error that exists between the prediction line and everybody else. And I'm gonna get there in a second, but I'll just tell you now, this T statistic, guess how we get it? B over standard error. That's how we test whether each predictor is a significant predictor or not. Hannah.
So could you say that the standard error of the intercept and the standard error of predictor, social support in this case, equals the error in our model? Or
No.
represents the error in our model?
No.
Why not?
Because they're not measuring it's not measuring variance, error variance.
Okay.
So are we essentially for the t-test doing the single sample? Are we doing a single sample t-test on the test statistic? Oh,
Yes,
yeah, we're not.
yes. Hold on, we'll get to the T's. So we're good with B and are we good with standard error? Questions about B or standard error? Yeah,
When you say like the T is B over standard error, is that conceptually or mathematically?
both.
Because I calculated that first one, it should be like the intercept T should be like 4 point something, but this one's 8. Like, I was just wondering why.
Shouldn't be. Truth could have made up this table.
Oh.
That's a possibility. Is 0.43 over 0.19 2.3?
It's 2.26 or something.
It's almost like double the T intercept the T. So that's why I was like saying.
Let me get back to you. Might have made it up. Yeah, sorry. Now, we don't, so for focus purpose, guys. Sorry, that's a screw up on my end, a big one. We don't care very much about the standard error of the intercept or the significance of the intercept. What we're really looking at is the predictor. Because the predictor is what we're interested, that's our model that we're specifying. We don't specify the intercept comes out for us. But what we're hypothesizing is that social support is a significant predictor of our outcome. So we have the next part, which is our confidence interval. Again, our confidence interval belongs to our B. We've done confidence intervals before. If we were to take repeated samples and the 95% confidence interval were computed for each sample, 95% of the intervals would contain the population coefficient. Now, what happens to that confidence interval when the standard error goes up? It gets wider. So that confidence interval is calculated using that standard error. The more variable that standard error is, the more variable that coefficient is, the wider our confidence interval is going to get. Then we have our standardized regression coefficient. Super important. Our standardized regression coefficient can be thought about in two different ways. The first way is it's the standardized slope. So just like our unstandardized slope, this is also the slope of the relationship between social support and self-esteem, but it's in standardized units. What are standardized units? You remember standardizing? Z-scores, which are what? Standard deviations. Good. So what this is saying is for a 1 standard deviation increase in X, we would expect Y to increase by 0.54 standard deviations. Yeah, for a 1 standard deviation increase in X, so in social support, we would expect Y to increase by 0.54 standard deviations. So all slopes are rise over run. Slopes in general are as X goes up by 1 blank, Y will go up by this much. The question is, what is the blank? If it's unstandardized, then it's as X goes up by 1 unit of X, Y will go up by this much of Y. If it's standardized, it says X goes up by 1 standard deviation, Y will go up by this many standard deviations. Okay, now, the other helpful part about beta is that beta can be thought about as the effect size or the magnitude of that predictor. Why? Not Y, but Y. What can beta range between if it's standardized? 0 and 1. What would a beta of 0 mean?
For every one standard deviation.
For every 1 standard deviation increase in X, Y goes up by nothing. What would that mean conceptually? There's no relationship. What would 1 mean? 1, 1, 1, 1. What does this sound exactly like?
Correlation.
Correlation. It is. A beta can be thought of exactly like a correlation coefficient. It's just the slope of a line. A 1 is a perfect slope that goes like that. A 0 is that. A 0.5 is there. So the benefit to beta is you can draw it. You can look at that number and right away, no matter what unit you measured in, you know how strongly social support and self-esteem, how strongly they're related, and you know in what direction. They're positively related. So as social support goes up, so does self-esteem, and pretty strongly, 0.54. Where have we seen that number before? It's Pearson R. Why? Because it's just the relationship between social support and self-esteem. The only difference is we drew a slope. We drew the line, okay? That happens only in simple regression. In simple regression, beta and Pearson R are always going to be exactly the same. Why? Because we take all our data points and we say, what's the correlation? 0.54. Draw the best line, 0.54. There's no other variable to contend with. So beta and Pearson R are exactly the same in a simple regression, which means, and this is going to help you tremendously when you get to multiple regression, if we were looking at correlation and you wanted to know how much variance in one variable was explained by the other, what did you do to the Pearson R? You squared it. So what could you do to the beta if you wanted to know? You square it. Now, in a simple regression, you already have it. You have it in where? You have it in big R squared. You have it here. But when you get to multiple regression and you have a lot of predictors, if you want to know the unique variance explained in your outcome by just that predictor, you can square its beta. Questions about these guys? You did fine with the standardizing, but by the way, this is a review from 308A. How do you get, if you care, how do you get from B to beta? The way it gets standardized is it multiplies our B, which is our unstandardized coefficient, by the standard deviations of X and Y. That's how you get beta. Thank you. You're so sweet. Now, this is really, these two things are really important. You understand how standardization works, but what's the impact on the regression equation? Two big impacts. What does the intercept become? 0. There's no intercept because that's the standardized average of Y. Everything gets standardized, there's no intercept, it becomes 0. And when you use your equation to predict a value, so if you're saying, hey, Hannah has a social support score of 4, what's her predicted self-esteem? If I'm using a standardized equation, can I plug in 4?
No.
No. What do I have to plug in? No, well, not the standard deviation. I heard it. How do I standardize a score? I heard it. Z-score.
Z-score.
Yeah, I have to plug in her standardized version of 4, which is a Z-score. Yeah, it's like I taught you that for a reason. Yeah, everything in regression has to match. If you have an unstandardized equation, you have to plug in raw numbers, unstandardized numbers. If you have a standardized equation, you have to plug in standardized values. When we get there in a second, if you have a centered equation, you need to plug in centered values, right? They always have to match, otherwise you're talking apples and oranges. So where were we going with this? So here we go, here are the two equations. So here's unstandardized, 1.94 plus 0.43, and here's the standardized equation, 0.54, just the beta. Generally, I'm gonna give you like a, how do we write this best practice? Because one of the confusing things becomes, well, when do I use which, right? For interpretation and for writing up like, oh, this was significant, we usually use the beta. Why do you think we do that?
Because it's standardized.
Yeah, but why does that make it the thing to use instead of the other one?
Everyone knows what it means when they read it.
Yeah, exactly. I can put a beta in a manuscript and you don't have to know how I measured any of my constructs. You don't have to like flip to my measure section and be like, ugh, how did she measure social support again? Everybody understands that beta goes from 0 to 1. 1 is really strong, 0 is no relationship. I can immediately understand the effect size by looking at the beta. Now, if you're gonna use an equation to plug in values, this would just be mean. Generally, if we're doing full equations, we're gonna use an unstandardized version. Cool. Now let's answer the question. Because she found a significant relationship, positive relationship, hypothesis 1 was fully supported. Usually I would, in a manuscript, use the beta and the actual p-value, and I can use it to predict outcomes. For someone with a social support score of 5, we'd predict self-esteem of, all I have to do is plug in the 5. I use the hat over the y because that's predicted y, not actual y. I predict them to have a self-esteem score of 4.12. And implications, social support positively relates to self-esteem. As social support increases, self-esteem significantly increases. If self-esteem is important to the recovery process, as she theorizes, her program should focus on providing social support. I want to skip this for a second. I want to go straight to centering. I'll go back to this in a second. Why did I put that at the end? That was silly. Where is it? There we go. I'm going to teach you one more thing, and then we'll demo and I'll talk APA. Best practice in regression. We're going to solve that problem of nobody weighs 0 pounds and scales don't start at 0. There's a best practice in regression that's called centering your data. As you get more advanced, as we get into moderation, there becomes other reasons to center the data. But in general, it's just a best practice to always center your data. So we're just going to always center our data from here on out. All right, so here's our original regression table that you looked at. And remember that our intercept is the predicted value of y when x is 0. So for someone who has a social support of 0, we would expect their self-esteem score to be 1.94. But what if we were predicting self-esteem from age? Then what would the intercept represent? The predicted self-esteem score when they were how many years old?
Just born.
Born.
0. But are you really 0 years old when you're just born? No. There's no such thing as 0 years old. It's not a meaningful value. Stats is numeric. It doesn't always take into account how actual life works. So what we're going to do to make that intercept more interpretable is we're going to center our predictors. And here is how that works. Here is our raw uncentered data. So here's our slope. What did we say our slope was? B is 0.43 or standardized beta is 0.54. And our intercept is 1.84. So that's the predicted self-esteem when social support is 0. What it means to center is to subtract the average x from all values of x. So here we have all the social support scores and all the self-esteem scores. What we're going to do is we're going to center social support. And generally what I do is I take the X and I do dot C. That's how I recognize that it's centered. The way that, what that does is it shifts, watch it shift. It shifts the scale and the line so that what is on the y-axis? The mean. So now this place that crosses the y-axis is the predicted score when X is average. So all we did was take the entire graph, the data points, the line, and the X scale, and we just shifted it all over by the mean. So that now that y-intercept is an interpretable value. It's the predicted score on y when X is average. Here's what it looks like. So now we're saying, hey, when social support is average, we would expect someone to have a self-esteem of 4.07. Did anything else in the table change? No, nothing else changes. It has no impact on the slope. It has no impact on the relationship between variables. It literally just moves it laterally by the mean. And the only purpose in terms of where we are now is to make that intercept more interpretable. Yeah.
So actually the T-score, the T value of T is from that.
That's why. Is that why? That's why. I kind of screwed up, but not a lot. Like 99?
Yeah. I mean.
Are you talking about the 2.30?
Guys, I don't want to focus there. You're gonna lose what really matters. Stop.
You can just round it.
Thank you. Stop. Stop. Yeah, Kayla. You subtract the mean of social support from every social support score.
Hey, Jess,
Yeah.
a question from the Zoomers. We had M asking, is there a reason that the degrees of freedom went from 14 to 13 or simply just different on this slide?
No, it's just different. It's 14. Are we good? Centering. That's all we're talking about. So it just moves laterally. Only thing that changes is what? Only thing that changes is what?
The y-intercept.
And that's what they want to see. They want to make sure that the leaf is all the way across because.
The intercept. Good. The intercept is the only thing that changes. It's the predicted value of y when X, and it's still, if you look at the graph, guys, it's still the predicted value of y when X is 0. You see that? It's just that it got shifted over so that that origin point is not really X equals 0 anymore. It's X being the mean. It makes it more interpretable. Now, why does that matter? Well, remember I said apples, apples, oranges, oranges. If you center your equation, you have to plug in centered values. Otherwise, you'll get the wrong predicted score. So if you have a centered equation like this, if you plug in that 5, like someone who has a social support of 5, you're gonna get a different answer for these two equations. So what do you have to do to that 5 first? Center it. How do you do that? Subtract the mean. You have to center the score before you plug it in. So let's look at that. Using centered output, what would the predicted self-esteem score be for someone with a social support score of 5? Here's the raw uncentered data. So we go 5 to here, but on the centered data where we moved everything over, it's here. So if we're using the centered equation, we can't plug in 5, we have to plug in centered version of 5, which is 5 minus the mean of X. And so we get the same answer as we got when we used the uncentered equation and plugged in 5. You just need to remember uncentered equation, uncentered input, centered equation, centered input. Unstandardized equation, unstandardized input, standardized equation, standardized input. But why are we centering?
Yeah, I don't.
2 reasons. One is it makes this value interpretable. Otherwise, this value doesn't mean anything. So it gives people just a rough understanding of like, big picture, when X is average, this is where we'd expect somebody. That's one of the biggest reasons, is like it's helpful to know where you predict someone to be on the outcome when somebody is your average X. More sophisticated answer is in a couple of weeks, when we get to moderation, centering will help with some of the issues that moderation creates. Yeah.
So do we always center, or is it only when?
Yes, we're always gonna center our predictors. That's why I just called it a best practice in regression. We're just always gonna do it. Where do you talk about centering in your write-up? In your data prep. So prior to specifying our model, all predictors were centered. You can add that line to every rep from here on out. Cool? Yeah.
Did the table specify if it's centered or not?
Good question. I think it's a best practice in your note to add data are centered. Yeah, that's a great question. I've definitely seen people just write it in the narrative and not have it in the note. But the idea generally is you want your table to be able to stand alone. So if there's information that would be helpful to make your table stand alone, put it in there. Same with here's another best practice. I put my model fit stats in my note. So again, so you can look at that while you're looking at the parameter estimates.
Hey, Jess. Evan's
Yes.
asking, where did we find the mean of X in this situation? The
descriptives.
The descriptives. Cool.
Descriptives, either descriptives, or you can just type mean X in R. Like you can literally write 5 minus mean variable. Yeah.
For data, we're not normal, we're median center, or we just like.
No, if your data were not normal, so much so that you wouldn't, if it's a tiny bit not normal, regression is pretty robust. But if it were super non-normal, then you probably would look at another alternative analysis entirely, and then you would be doing this. Yeah, centering your predictors doesn't fix normality issues. Yeah, because all it's doing is moving things laterally. Cool. Now I'm gonna go back to the writing, and then we'll dive into the demo. Writing a results section. So how do we organize our results and our tables and figures? So we have 2 parts of the results section. One is our narrative, like what you're actually writing up, and one are the tables and figures. This slide gives you a good overview of everything that needs to be in both of those sections. So again, tag this slide as something to come back to. In the narrative section, what you ran and why you ran it. Any missing data and what you did about it. Again, I don't think that's going to be an issue. You can just say there were no missing data. Any important cleaning notes and the final sample size. So I removed X outliers or I removed no outliers. Final sample size was blank. Descriptive stats. When you have tables and figures, you don't need to necessarily say all the descriptive stats. You can say, descriptive statistics and correlations are, table 1 contains descriptive statistics and correlations. That's fine. Only need to really talk about them if there's something of note to talk about. Oh, I wrote that. Say you ran them and point people to the table. Discuss only if needed. Assumptions, bless you.
Thank you.
What they are, how you checked, and whether they were violated. Inferential stats, model specification. So model 1 specified blah, blah, blah. Model fit, bless you. Model parameters and whether they supported your hypotheses or not. And then summarize your key takeaway, not discussing the implications in the results section. Results are telling us the results. The so what, the implications, that goes in the discussion section. Tables and figures that you need. Tables, you need descriptives, means and standard deviations. Correlation table, you can put those together in the APA table that I showed you on Tuesday. You need a regression table. The regression table should have, the reason I just say regression table is because you can put the R-squared in the same table as your model parameters. You just add a column at the end that says R-squared. You can even add the F stats at the end if you want to, okay? But they can all go in one table. Figures, you need a model figure with your results in them, and graphs where appropriate. This won't come up, I think, until we get to moderation. So when we get to moderation, you will need simple slopes graphs. You don't need those yet. So now we're like here. So let's look at what that would look like for a simple regression. So let's do it, but let's do it the demo first because it pertains to the demo. So let's actually analyze that data. And then we'll look at the results. All right. Oh yeah, do you guys want to do lasso regression instead? Just kidding. It's not what we're doing. All right, here we go. Let me clear out all this junk. A lot of it. So same study we did. What am I today? Oh, I'm nothing because I have no packages. You're laudable. Oh, you're superb. So same data. This is the what leads people to want to lead in Reddit groups. And last time we looked at the correlation between a self-efficacy and desire to lead. Now we're just going to run that as a simple regression instead of a correlation. So instead of being a dual arrow, it's going to be a, share this instead. So instead of being a double arrow, I've got a couple here. We're going to look at desire to lead, but we're going to look at self-efficacy, leader identity, and group support. And you'll notice same relationship, but instead of a double arrow, now we're working with a single arrow because it's a simple regression. So desire to lead regressed onto self-efficacy. Self-efficacy positively relates to desire to lead. The only thing that makes the arrow one-sided is that it's a simple regression. We're assigning theory to it. We're modeling causality, even though it's not a causal analysis. And then this is really important. What is our statistical hypothesis? Well, what would the null hypothesis be conceptually? Said it. No slope, what does that mean conceptually though? No relationship. The null hypothesis would be that self-efficacy and desire to lead are not related. And if they're not related, that would mean the slope would be flat. And what would the coefficient or parameter estimate be if the slope were flat? Zero. Good. So our null hypothesis for any predictor is B equals 0. And our alternative hypothesis is that B equals something other than 0. Okay, good. All right, now let's go to us here. All right, so here we go. We've got our scatter plot. We're going to check assumptions. We already looked at skew and kurtosis last time. We've got self-efficacy and desire to lead. Here's our scatter plot. So to make that scatter plot, I first specified the relationship here. So there's the data set. And here are the two variables that I'm going to check. And then this is just about making that scatter plot pretty. So I added a line. This here, method LM is linear model, color red. I just said, go ahead and add a line to it. I don't have to add a line, it just helps me visualize that scatter plot. Does it look like there's somewhat of a linear relationship? Yeah, thanks, Quinn. Yeah, as self-efficacy goes up, in general, desire to lead goes up. One thing that can help you figure out if there's a relationship is take two different segments. When self-efficacy is low, what happens? People are generally low in desire to lead. Is anyone high? No. But when people are high in self-efficacy, you have high, you also have some low. That generally shows like no one's over here. That's some sort of linear relationship going on. Now we need to check whether the model, yeah, go ahead.
What's the gray shadow?
Error. Yeah, some degree of error. Now let's look at homoscedasticity, heteroscedasticity. So this is whether, reminder, we've revisited this before, but this is the degree to which the model works. I should say specifically, this is the degree to which the error is constant, as in the same, across all levels of the predictor. I can already tell you it's not going to be. You can already tell me it's not going to be. Why? Because down here, it's all pretty close to the line. But up here, you've got people way above and way below. But let's actually look at a residual plot. So the first thing that you need to do when you want to see a residual plot is you have to specify the model using like the basic linear model code, which is just LM. So we're going to use LM and we're going to regress desire to lead onto self-efficacy. We're going to save that model. And then we're going to create a residual plot using that model. And here we go. So here are the fitted values. So these are the different levels of the predictor. And here are the residuals. What does that green line represent?
The,
No residual,
No error.
no error.
This is an error plot. It's plotting values of the predictor against degree of error from the line. The green line in the middle is perfect fit. Above and below is just whether it's over predicting or under predicting. What do you notice?
Yeah, less error on one side and then more error on the other.
There you go, more specific. Yeah, than that.
Error increases with self-efficacy increases.
There, good. The model the amount of error increases as self-efficacy values go up. So the model works better for who? Low values of self-efficacy. What?
This is mine.
Oh, go, you're fine. That's really important. So you can't just say like it's heteroscedastic or it's different, because when you're writing your implications, that's not enough. When you get to the implication section, you have to know who it's working better for and who it's not working better for. So yeah, are you gonna stop? No, but you want to interpret your results to some degree with some caution, because it may work as people get high in self-efficacy. Self-efficacy may not be enough to explain desire to lead, because people high in self-efficacy, some of them really want to, some of them really don't. Whereas on the low end, it does really seem to be that if your self-efficacy is low, you do not want to lead. So you still learn something from the model, but it's with like a little asterisk of hold on. That's why you got to get to know your data. The story and the answer is in the data. Yeah.
Do you also want to take into account that there's not a lot of people in the low self-efficacy area?
There are not as many, but there's not nobody. I mean, there's like a decent chunk of people. It's just that you have nobody, you have all the people who are in the low area, like up until here, nobody is above a 5 in desire to lead. But that's important. That's like actually an important finding. I would argue that the model, there is some truth or utility, I shouldn't say truth, utility in the model that as self-efficacy goes up to some point, desire to lead, like self-efficacy does impact your desire to lead, but when we get to the higher levels of self-efficacy, that is not enough to tell us whether someone's gonna lead or not. Which is why I guarantee you his final model was not a simple regression. Yeah.
So when we're reporting this and talking about our assumptions, do we say that it, from the scatter plot, it seems that the model fit may work best for those that are lower in self-efficacy?
Yeah, that's fine to do. I would say if this were, yeah, I think you would probably do that. I've also done it where I just say like the model, the data are heteroscedastic, which may have implications for our interpretation of the model. And then I dive more into it in the discussion.
Got it.
I would say for our class, since there is no discussion, it would be worth pointing out how it's heteroscedastic. Yeah. And then you can test that statistically, which is literally testing, is the variance, are the residuals constant across levels of the predictor? And you already know from looking at this, the answer is going to be no. The answer is way no. So chi-square 35.81, chi-square 1, 35 point p less than 0.001. Okay. So I would say something like data appeared heteroscedastic, value, higher values of self-efficacy demonstrated far greater error than lower levels of self-efficacy. This was, this was supported by a non-constant variance test or a Bruce-Pagan test report. All right, let's do the regression. So here we're going to use lin-reg. Notice, by the way, that up here, LM, we actually already ran the linear model. We just ran it with really ugly code. So this model here, if I printed it, there's the model. There are your coefficients. There's the intercept, there's the B. But there's other stuff you want to see. And it doesn't give you everything in the basic model. So I like to use lin-reg, which comes from JMV. Dependent variable, covariates just means any of your predictors. A reminder, just like ANOVA, these are the predictors you want available. These are the actual predictors you're using in your model. When we get to building hierarchical models, we'll play with this a bit more. Model test equals true. That's gonna give you fit. Standard estimate, that's gonna give you what? What would your standard estimate be? What is the estimate of the parameter that is standard?
Easier.
No. Standard.
The standard
Just
deviation.
say it, don't mime it. Let's all act it out, like JJ. Ready? What is it? Beta! Yeah. There's only one standardized estimate that you get. It's the most important estimate that you get. Beta. Good. This says I want beta. CI, I want a confidence interval. What does the confidence interval belong to? It belongs to B. Go ahead, follow the model. Look at how beautiful it is. So pretty. R squared, what does that mean? 43. We forgot to round over break. Okay. 43% of the variance in desire to lead can be explained by our model, which only has one thing in it, which means it can also be explained by self-efficacy. What is this R gonna be equal to?
Correlation.
Correlation.
The beta and the Pearson R, the correlation, because it's simple. Good. And beta squared is gonna be equal to what? R squared. Good. Nice. So here we go. Here's that really weird intercept that makes no sense. Negative 0.20. That's the predicted desire to lead on a scale of 1 to 7 when self-efficacy is 0, which doesn't exist because the self-efficacy scale also starts at 1. So let's center our predictors. You don't need to derive the mean, you can just ask. So I always, the way that I name my centered variables is I just add .c to the end. So self-efficacy .c. All I do is I take self-efficacy and I subtract the mean of self-efficacy. And then in my data, I'm gonna get a column at the end that says self-efficacy .c. And I'm gonna run the model again, but with my centered data. Nothing changes in my fit stats. Nothing changes in my table except my intercept. Now, the predicted desire to lead when self-efficacy is average is 4.10. Cool. And you know how to, here's the APA regression table. Again, you have to start with the LM function, and then the function is APA reg table, but I'm going to show you what it looks like. It's not, it's even worse than the correlation table. Sorry. Oh, it does put the fit in there for you. That's cool. Okay. So here's what it looks like. Not beautiful. It needs some work, but it's a nice start. Yeah. So you'll see what it does is it gives you the R squared in there, which is fine. You can put your R squared in the regression table instead of having to have a separate model fit table. That's all right. So let's look at what it looks like all together, and then I will let you go. So, type of analysis and why you did it. Linear regression was used to test whether self-efficacy amongst Reddit users influenced their desire to lead a Reddit group. How can I make this better? Maybe get rid of influence and use less causal language. So something like linear regression was used to test whether self-efficacy amongst Reddit users related to their desire to lead a Reddit group, okay? Then all your cleaning stuff. There was no missing data and no outliers were removed, resulting in a final sample of 323 participants. Table 1 contains descriptive statistics and correlations for all study variables. I gave you an example of what it might look like if you did take out people down there, but that's probably not going to be an issue in your DAs. Assumptions. Prior to model specification, all assumptions of linear regression were checked. A scatter plot supported a linear relationship between self-efficacy and desire to lead. Although a histogram of desire to lead appeared positively skewed, skewing kurtosis values were below 3 and 10 respectively, supporting sufficient normality. Fitted residual plots showed some degree of heteroscedasticity, and a Bruce-Pagan test confirmed the assumption of homoscedasticity was violated. There you go. Specifically, there appears to be more error variance for higher self-esteem values. As such, model results should be interpreted with caution, particularly for those with high self-esteem. Cool. All right, to test our hypothesis, we specified a simple regression model with self-efficacy predicting desire to lead. This model was significant. Self-esteem explained 43% of the variance in desire to lead. Model fit statistics. An examination of regression coefficients confirmed support for hypothesis 1, self-esteem positively related to desire to leave, beta and p-value. Table 2 contains all model parameters. In summary, study findings support the idea that individuals with higher self-esteem are more likely to desire leadership roles in groups to which they belong. All together. Cool?